Hello, I'm Naseer Rashid, and I'm going to discuss the design of a carbon-neutral airport. I had the privilege of working on this project with Joel Hanna, Danielle Hettmann, Saleh, and Cihan Yilmaz. Air transportation is a critical part of the United States economy as a part of movement of goods and people for economic growth. In 2010, it generated $7.4 billion of profit. CO2 is a product of hydrocarbon combustion. The amount of gases emitted is related to the amount of fuel consumed, which is a function of the engine fuel efficiency and the amount of time the engine is running. Aircraft engine emissions consist of about 70% CO2 and just under 30% H2O, with the remainder of pollutants making up less than 1% of the total. When evaluating solutions for emissions reduction, the airport manager has to consider four main factors. The first is the maturity of the reduction strategy, or how reliable it is. The second is the amount of control the airport manager has over the solution. The third factor is the amount of time it takes to implement the strategy. And the final factor to consider is the amount of emissions the strategy will reduce. The problem we face is the airport manager needs to achieve carbon-neutral growth while operating a business with limited control. The notional graph by the FAA shows the baseline level of emissions and projections to 2050. With unmitigated growth, carbon-neutral growth is unattainable. Within the boundary of an airport, there are four categories of emission sources: aircrafts, ground support equipment, ground access vehicles, and stationary sources. A crucial part of measuring emissions is the landing takeoff cycle. This refers to the number of aircrafts that land and take off. The landing takeoff cycle is divided into four segments: approach, taxi idle, takeoff, and climb out. Every aircraft has a different fuel burn rate and operating time for each mode. This cycle is used as a baseline for emissions calculations. As a case study, we use Dulles International Airport. Dulles is owned and operated by the Metropolitan Washington Airports Authority and sits on a 12,000-acre property. Since its opening in 1962, the number of passengers and flights has continued to increase. The growth rate for total flights has averaged 2%. Our work focused on providing the airport manager a trade-off analysis to limit the impact of aircraft carbon dioxide emissions on global climate by achieving carbon-neutral growth by 2020 and net reduction in emissions by 2050, using 2005 as a baseline. In order to provide a trade-off analysis on reduction strategies, we created an airport inventory tool. The tool is designed for use by the airport manager. It calculates baseline emissions. The tool provides projections based on those emissions and models the impact of design alternatives. The home screen of the airport inventory tool gives an overall picture of the airport. The number of LTOs and supporting equipment for aircraft is available, as well as the number of passengers, including employees, and the total fuel consumption for each stationary source. For aircrafts, the time and mode and fuel burn rate for each segment, the number of engines and the number of LTOs, and the emissions index for each fuel type were used to calculate the total emissions. Based on a European Commission study, a conversion factor was applied to get the total CO2 output for APUs. The data screen for aircrafts shows each aircraft, their engine type, number of LTOs, time and mode, and fuel burn rate for each mode. The screen also shows the total fuel consumption, total emissions, and APU emissions. To calculate ground support equipment emissions, time in use, horsepower, and load factor for each service item were used along with a CO2 factor. The first data screen for GSE shows each aircraft and its assigned GSE group. GSE groups are based on GSE data from the Dulles Airport Environmental Impact Study. There are 11 GSE groups total. Group A, for instance, consists of 14 GSEs, leading to 354 kilograms of CO2 emitted per LTO serviced. For ground access vehicles, the distance traveled by each vehicle, fuel economy of the vehicle, and the emissions index of the fuel consumed were used to calculate total emissions. The input screen for ground access vehicle accepts inputs for the number of passengers and employees. The number of O&D passengers is then generated along with the number of passengers by vehicle type. At the bottom of the GAV screen is the employee information. This screen is distinct because it was only broken up into diesel and gas vehicles. Stationary emissions were calculated using total fuel consumption and the emissions index for each source. This was possible because stationary emissions are already being reported under the Clean Air Act. On the stationary input screen, the user inputs the total fuel consumption for each source. The total fuel consumption and total emissions for each fuel type is shown, as well as a breakdown of emissions by fuel type. Using emissions data calculated from the AIT, it was determined that the largest contributor of emissions is ground access vehicles with 291 million kilograms of CO2 annually, followed by aircraft with 255 million kilograms. GSE and stationary are smaller contributors to emissions, with a combined 45 million kilograms of CO2. Breaking down annual emissions to reflect CO2 per passenger shows that each passenger accounts for approximately 26 kilograms of CO2. Design alternatives have been identified to reduce emissions by source based on emissions reduction strategies from the Airport Cooperative Research Program. Design alternatives from the ACRP were scored based on utility function and weights, agreed upon by our project sponsor and airport stakeholders through a Delphi process. Each design alternative received a score in each utility area, with 4 being the best and 1 being the worst. Implementation time is defined as the time needed to completely implement this reduction strategy. Maturity of reduction strategy identifies the readiness of the strategy, while airport control measures the ability of the airport operator to implement and influence the strategy. Emissions reduction, identified as the most important in the utility function, is measured by the annual reduction by the proposed strategy. Looking back at CO2 per passenger, we have determined how much CO2 each design alternative would reduce per passenger. If each alternative was implemented in a single year, CO2 per passenger would be reduced by 18 kilograms of CO2, but there would still be 8 kilograms of CO2 per passenger that would need to be reduced in order to have complete carbon neutrality. Using baseline emissions data from AIT, we've created a projection for airport emissions from 2005 to 2050 using a 2% growth rate for airport operations, shown in black. As shown in red, if nothing is done to mitigate the emissions, they will continue to rise and the airport will not meet carbon neutrality by 2050. Implementing all the design alternatives we've analyzed suggests that carbon neutral growth can be achieved with a 2% growth rate. This implementation assumes that all design alternatives would be implemented at full capacity starting in 2013, and emissions reduction would be immediate, with the exception of alternative fuels, which begins in 2018. We've also modeled an emissions projection using a 4% growth rate for airport operations. This projection once again assumes that all design alternatives would be implemented in 2013, with the exception of alternative fuels. With a 4% growth rate, the goal of carbon neutral growth would not be achieved. Realistically, it wouldn't be feasible to implement all design alternatives in 2013 due to technological and financial constraints. For this reason, the team recommends 3 design alternatives be implemented immediately to begin reducing airport emissions. Since aircraft and GAV are the 2 largest sources of emissions, recommended alternatives focus on these sources. Based on utility ranking, we recommend to the airport manager that aircraft exchange APUs for electric ground power while at the gate. Another high-ranking alternative is implementing alternatively fueled taxis by converting current vehicles to hybrid vehicles. This would be especially powerful at Dulles Airport, since the rights to service Dulles Airport passengers is controlled by the airport manager.